Okay, great. Well, yeah, as Deep just said, I'm Ross Dempsey. It's my first year here as Pappalardo Fellow. It's a real joy to be here. I'll be telling you about my research in particle physics, all under the heading of colliders from first principles. But to tell you what that title means, I actually want to start somewhere rather far afield from particle physics in chemistry. So in chemistry, we study all sorts of substances, chemicals, and the molecules within them, and all sorts of properties of these substances and these molecules. To give you one random example, if I take water, it has H2O molecules. That molecule has some bond geometry, some length between the atoms and some angle between the bonds. Now, things like this are almost always measured empirically, and a huge number of these empirical measurements are collected in this rather famous book, the CRC Handbook of Chemistry and Physics. Now, I don't own that book, so I had to get a picture off the internet, and the person on the internet thought it was important for you to see that it weighs about 6.5 pounds, and it's significantly larger than a dollar bill. So it's an impressive compendium of knowledge about the world. But in physics, we know that all of these systems are governed by a single unifying principle, namely quantum mechanics. And there's a single fundamental equation, Schrödinger's equation, that in principle should give rise to all these phenomena collected in this big book. And to show you one sort of toy example of actually doing this, here what I'm doing is solving Schrödinger's equation for the electron cloud around this H2O molecule, and then moving the atomic positions to slowly relax to the equilibrium configuration, where you see we'll almost reproduce the correct measured bond geometry. So that's the idea of ab initio physics, of starting from the defining equations and working your way all the way to the experimental measurements. It's sort of a gold standard in my mind for what theoretical physics can do. And with that in mind, I now want to turn back to particle physics. So in particle physics, we have our own great big book of data. It's called the PDG Review of Particle Physics. This is a copy I found lying around MIT, and here I'm giving you the banana for scale, courtesy of the MIT Banana Lounge. And almost all of the information in this book comes in some way from the collider experiments that Jillian was telling you about. These engineering marvels where we collide particles at high energies and do very complicated analyses of what comes out to understand the fundamental interactions governing those particles. And so I want to ask now, what can we do to try to make that journey all the way from the fundamental equations defining these particle interactions? These are the equations of quantum field theory, a generalization of quantum mechanics. How can we go all the way from quantum field theory to those kinds of measurements? Now, there's a long tradition of doing so in terms of Feynman diagrams. Feynman diagrams work fantastically well when they work, and they work for a class of theories that are called weakly coupled. So they're in some sense close to being classical theories. But in our world, we also have quantum field theories that do not have this property. A famous example is the theory that describes how quarks and gluons come together to form the proton. That theory, called quantum chromodynamics, or QCD, is inherently strongly coupled. And so to treat theories like that, we need methods that go beyond Feynman diagrams. So I'll be telling you today about my work in two of those methods called non-perturbative techniques that work for these strongly coupled theories. And these, for me, are the lattice and the bootstrap. So let me start by telling you about the lattice. So lattice field theory is one of the oldest ideas for taking quantum field theory and studying it non-perturbatively. And most of lattice field theory over the past 50 years has been focused on Euclidean lattice field theory. The idea there is that we take both space and time, which are here horizontal and vertical respectively, and we break them up into discrete chunks. We simulate matter fields on the sites of some mesh like this and force fields on the links. And then very crucially, in that time direction, we do a mathematical trick where t becomes I times t. Time becomes imaginary time. And that's what allows us to take a quantum field theory and turn it into a classical sampling problem, which can be solved relatively efficiently. I'll be instead today focusing on a different approach called the Hamiltonian lattice. In the Hamiltonian lattice, we still break up space into chunks, so that's still the horizontal direction here, but we leave time continuous and we leave time real. So that opens up the possibility of simulating processes that happen over real time in that time, much like the processes that happen inside of particle colliders. So the trick to this is that instead of going to a classical sampling problem, in the Hamiltonian lattice, we go from a quantum field theory to a quantum many-body problem, which Lena just got done telling you are quite difficult. So that's one of the reasons that the Hamiltonian lattice, while it's been known almost as long, has only really come into its own in recent years. And to give you an example of what the Hamiltonian lattice can do, I want to set a target, and that will be the Schwinger model. So this is an old example of quantum field theory. In fact, I want to take you back to 1962 here in Cambridge. So Neil Pappalardo would be a sophomore at MIT. Jane, I'm told, was across the river at BU. And then Julian Schwinger is up the road at Harvard. And he's thinking about quantum field theory, which is a new idea at the time. It's becoming clear already that whatever theories describe the real world are going to have to be quite complicated. And so he's asking himself, what are the simplest quantum field theories we can write down? And he comes up with this, which is now called the Schwinger model. The idea is you take one spatial dimension, and you have an electron, its antiparticle, the positron, and a photon, which carries the EM force between them. So it's sort of a bare minimum example of an interacting quantum field theory that describes particles interacting. And Schwinger reasons that in this setting, what will happen is the electron and the positron will come together and form a bound state, glued together by the interactions carried by the photon. So this is much like in the real world how quarks and gluons come together to form a proton. So when you see this diagram, think of it as a toy proton in our toy model for QCD. Now, one thing we can do is take this model and try to study it on the lattice, as I was telling you. And so to do that, we would take this equation Schwinger wrote down and write down a similar one I won't go through in detail, but it describes all the same physics. The photon kinetic energy, the electron kinetic energy, the mass, the interaction, all the same physics is there, but broken up into a discrete setting. And so then the setting is this lattice where I have electrons and positrons on sites, electric fields carried by the photon between them, and there's some lattice spacing A that we want to take smaller and smaller to approximate the continuum limit physics. So before we delve into that lattice, let's take one more gem from Schwinger's work. Schwinger not only wrote down this model and figured out what we'll do qualitatively, he actually managed in one very specific limit to solve it quantitatively. He realized that if the electron is massless at this little m equals 0, then he was able to mathematically calculate what the mass of this bound state will be, our toy proton. And the appropriate units, that mass is 1 over the square root of pi. So in this one special limit where the theory is solvable, sort of our benchmark limit, Schwinger gives us the exact right answer. And let me say briefly how that comes about. So if you have this model without interactions, if you turn off the coupling between photons and electrons, then the model has two rotational symmetries. They're called the vector symmetry and the axial symmetry. And crucially, they're mathematically linked in this inextricable way, vector and axial. But it was realized that when you want to turn on interactions, it's very important to favor one of those two symmetries. This was realized by Adler, Bell, and the late MIT professor Roman Jakiv. And it was realized that once you favor one of the two symmetries, conventionally the vector symmetry, the other one, the axial, is left broken. We call this an anomaly. And the way that symmetry is broken leads you to an equation from which you can just directly read off the mass of this electron-positron bound state. So somehow the breaking of a symmetry is crucial to telling us the answer to this physical problem. Great. So with this in mind, let's turn back to the lattice and ask what the lattice can do for us to simulate this model. So here I'm showing you a rendering of a simulation of this electron-positron bound state. Here's everything's very smooth, which means our lattice is very fine, approaching the continuum limit. But I actually want to zoom in on this lattice and look inside, look at the microscopic details of how we're doing the simulation. So when we zoom in on this lattice, what we see is this nice sort of bifurcated structure with a twofold pattern. Now, if you move the whole thing over by two sites, it will look the same. And that's a symmetry, an unbroken symmetry. That's great. That's translation symmetry. That corresponds to the fact that the laws of physics here are the same as the laws of physics there. Every lattice model that's been written down has that property, going back to the 70s. So that's great. But if you only keep track of that symmetry, as was done in the 70s, then when you do a first sort of benchmark calculation trying to approximate this mass, you don't do too well. In fact, here I'm showing you 1 over the mass squared, which ought to be equal to pi. That's the answer Schwinger gave us. But the answer you get from this sort of first pass calculation is 1.69, not very close to pi. Now, the model's not wrong per se. You can work harder, do bigger calculations, put it on bigger computers, eventually get that number closer to pi. But it reminds me of this old Irish joke where a traveler asks a man, "How do I get to Dublin?" And the man says, "Well, I sure wouldn't start from here." So we like to start somewhere better on our journey towards pi. And to do that, I want to look at one-site translations. Now, if I do a one-site translation, this lattice looks different. That's a symmetry that could have been there, but is broken. And we just got done talking about how the axial symmetry sort of was there, but was broken. And so the question I asked with my collaborators is, what if these things are related? What if the breaking of the one-site translation symmetry is associated with that axial symmetry that's been known for a long time? And we asked ourselves, can we write a Hamiltonian that makes that analogy mathematically precise? And the answer is yes. We can adjust the Hamiltonian such that this is so. And when we do so, our new approximation to pi is 3.146. So we're significantly closer and in a much better position to simulate this model, both at this exactly solvable limit and in non-trivial parameter regimes as well. So how does this work? Is it some complicated deformation? Actually, no. So what we published with these co-authors, including my PhD advisor, Silvio Pufu, who was himself a Pappalardo fellow many years ago, what we found was that all you have to do is take the mass of the electron on the lattice and shift it by some negative amount proportional to the lattice spacing A. So that goes away in the continuum limit, but it's crucial when you're still on your computer doing your finite simulations. That's how we get this improved fidelity to the true physics. So we've been able to do lots of fun stuff with this. Here's a plot from a recent paper where we studied the model with two flavors of particles, kind of like the up and down quark in the real world, and studied its phase structure in a very precise way. Here's another example doing a simulation over time. So the x-axis here is time. And what we do is fill the vacuum with some electric flux energy density, and then watch that sort of evaporate into electrons and positrons. And in orange is the exact right answer for how fast that decay happens, thanks to Schwinger. In triangles is a simulation without this mass shift, and in circles is a simulation with it. So you can see, especially for real-time processes, it's essential to use this technique to get high-fidelity simulations. So that's exciting, and there's many horizons for what we can learn about physics in one space dimension using this technique and related approaches. So to show you some other examples of work, here's a group in Japan using this mass shift to combine with advanced classical methods to study critical points of this model. Here's a group at University of Washington, again using the mass shift combined with other many fancy methods to put this model on actual quantum hardware and do a true quantum simulation of it. I personally have been working on non-abelian gauge theories, which are closer mathematically to QCD and entail some intricate structure on the lattice. And then one horizon I'm looking at while here at MIT is to actually do full-scale quantum simulations of collisions in this model. This is really exciting, but I want to emphasize that doing something like this is currently quite limited to one space dimension. To scale this up, to do quantum simulations of the collisions that happen in real three-dimensional colliders is going to take a lot more work from many different directions. And so I now want to pivot and tell you about something I've been doing during my first year here at MIT, focused on three-dimensional colliders. And that's going to go under the heading of energy correlators. So to go back to the detectors Jillian was telling you about, you have these massive apparatuses, thousands of detectors, but I want to consider the theorist's idealized version where we actually have only just two detectors in this whole apparatus, two sort of cameras that count how much energy comes in some direction. They're going to be displaced by some angle chi. And we want to ask, what is the correlation between the energy that one camera sees and the energy the other camera sees? This is a probe of actually lots of very interesting physics. And this is a probe that's actively studied and measured in real colliders. So here's a plot from Ian Stewart's group where they take, in these black points are data that's actually measured from an experiment. And then the other curves are ways of computing that in QCD using Feynman diagrams and related techniques. But for my purpose, we want to do this calculation, as we're saying, ab initio, sort of from the beginning. And for that, we're going to need to turn to a theory a little bit simpler than QCD, but still a three-dimensional, 3+1 dimensional gauge theory. And so our target is going to be not QCD at the moment, but something called n=4 super Yang-Mills. This is a frequently studied sort of toy model for quantum chromodynamics. But if you think of QCD as kind of an irregular object in the space of all these theories, kind of misshapen, we love it because it describes our world, but mathematically it's not so isolated. n=4 super Yang-Mills, by contrast, is almost like a Platonic solid. It's very rigid, it's very special. And so we have lots of mathematical traction for studying this object and this theory of interactions. So we want to try to figure out what the energy correlator is, how a collision process looks in n=4 super Yang-Mills. How to do that? Well, we're going to use a very different kind of simulation technique than we had before, and it's called the bootstrap. For the bootstrap, I like to compare it to this lovely quote from Ada Palmer in her novel *Two Like the Lightning*, where she describes a character as someone who loves the universe so much they spend their whole life talking about all the different ways that it could be. Now, that's a lovely sentiment. The bootstrap, I think, is a way to take that sentiment and make it mathematically rigorous. What we want to do is we want to ask the question, not what is the energy correlator in n equals 4, because that's hard. We want to ask, what are all the possible ways the energy correlator could be? More precisely, what's the maximum and minimum value of the energy correlator at some angle and some coupling for this theory? And we want to ask that maximum minimum subject to the constraints that come from all the special properties that make n equals 4 this beautiful Platonic solid-like object. And what are those properties? Well, one of them is supersymmetry, relating the bosons and fermions that Jens was telling you about just before. One of them is conformal symmetry, which tells me that I can reshape and rescale space and time, and I'll recover the same kinds of physics. And a third, which is very universal, is unitarity, which says that probabilities in quantum mechanics, which come from norms of states like this, should always be non-negative. So these are all very important principles that sort of isolate n equals 4 at super Yang-Mills as the special theory, and we want to use them to constrain the energy correlator. How will we do that in practice? Well, the answer is linear programming. So linear programming is a technique that goes back many decades, and it was developed in the context of business. The question would be, if I have many variables like different machine settings in my factory, how do I maximize profit subject to the constraints of my factory capabilities? We're going to use it in a slightly different way here, which is to say that we have all these variables, which are called lambda squared on the slide. They describe in a principled way all the things we don't know about n equals 4 super Yang-Mills, all these unknowns that we'd like to know. Individually, we don't know what they are, but what we can ask is, okay, what's the maximum value of the energy correlator, which can be written as a function of those lambda squareds, subject to the constraints, these linear constraints that tell us about supersymmetry, conformal symmetry, and unitarity. And so I can use this linear programming apparatus to put these bounds on what the energy correlator is allowed to be. Now, I'm showing you just 2 lambda squareds. In practice, there's actually going to be tens of thousands that approximate a whole infinite continuum, and there's going to be hundreds of constraints on them. So you get this high-dimensional complex polytope. But thankfully, there are highly efficient numerical methods that we can put this on a computer and figure out the sort of shape of that polytope. And that's what I'll show you here. So to walk you through a rather complicated plot, on the x-axis here, we have the coupling, G, which is smaller towards the right. And so towards the right in this gray surface, I'm showing you the answer to our question, the energy correlator, from Feynman diagrams. You can see that U shape that we had on the previous slide. Now, on the left, we also have the answer at very strong coupling due to a special relationship between this theory and quantum gravity, which I won't go into. But just to say, we have these 2 limits, very weak coupling and very strong coupling. These have both been understood for a while. Anybody can show you these. But what we don't have until now is what happens in between. And so this is what only this method can show you that I developed with these co-authors. The bootstrap allows you to put upper and lower bounds on the energy correlator going between all these couplings and beautifully interpolate between the weak and strong coupling limits, telling you for arbitrary couplings how this theory will behave in a collider setting. And so we fill in this missing picture and understand in an important way how this theory works. So with that, let me wrap up just by saying there's lots more to understand here, lots more interesting questions, and hopefully more interesting solutions as well. And I'm so grateful to be here studying these questions. I want to end with a massive thank you to Neil and Jane Pappalardo for enabling me to be here and keep working on these things. And I'll stop here for questions. Thanks so much.
Thanks, Ross. OK, so we have lots of time for questions. Bob, can you use the mic that's on the stand right in front, right up there? Yeah.
Any thoughts about how to go from n equal 4 supersymmetric gauge theories to the interesting case of QCD in 4 space-time dimensions?
Absolutely, absolutely. So a key technique we're using here, as you saw, is conformal symmetry, which is special to some of these highly supersymmetric settings. And so the techniques will not directly transfer to QCD. However, there are similar style techniques, also called the bootstrap, but other varieties of bootstrap that can apply to non-supersymmetric gauge theories. These are being studied quite a bit. And so the hope is probably that eventually some of these techniques can be used to constrain real-world correlators in similar ways. But that's probably more than a few years down the line.
Other questions? I've been scolded for not using the mic on the question, so.
So in in the second part of your talk, you gave us an idea of how you actually did the calculation with the linear programming.
Yes.
I mean, you showed it was 2 lambdas. There's actually 10 to the 4th, but we got the idea. But in the first part of your talk, at the end, you had a numerical result for real-time dynamics with and we heard from Lena and Jens about the challenges of actually doing computations with fermions and theories like this. So how did you actually manage to do the calculation?
Great question. Thank you so much. Yeah, so right, Lena was telling us how when we want to solve quantum systems that have something like here as n equals 64 sites, you're talking about the number of quantum states of order of the number of particles in the universe. It's going to get pretty nasty. We have a really special trick we can use for one-dimensional systems. That trick sort of leverages the structure of quantum entanglement to sort of find a needle in the haystack, find the part of that huge number of states where the actual low-lying states that govern this process will live. And so that all goes under the heading of tensor networks. Some of my work has been related to taking tensor networks which were developed for other systems and revamping them so they can apply more naturally to systems of interacting particles and gauge fields. But that's the key technique we use, tensor networks.
Thanks. 2 questions. The first one, this formula, it looks like a first-order correction, and I'm thinking of my experience in computational fluid dynamics or other fields where you can use a Taylor series to show how a lattice discretization is related to the continuum model. So have you been able to extend that to the next order and get 3.14 ...
So I should say, the 3.146 number comes from even just the first pass calculation. With techniques like the ones you're using here, you get many, many more digits than that already. But to answer your actual question, yeah, so it's definitely interesting if you get to ask, could we do better by extending beyond this, this first order shift in the mass? I would say the guiding principle that we used here, the symmetries, kind of runs out at this first order. But you can definitely ask empirically, can we tune this mass prescription so that things will converge even faster towards the continuum limit? Some work has been done on that. At the moment, we don't have a principled way of finding the higher order terms like we have for finding this one, but it's an interesting question.
I want to ask you, several years ago, there was a group in Italy, and they were developing, special computer to solve QED, and they were. So this is a long time ago, so I don't remember exactly, but they were claiming to finally calculate also the mass of the quarks or some things. So what has been this progress? And then within that, also, I would like to ask you, I'm not a specialist in particle physics, I'm a condensed matter. So what is the role of the Higgs? Because if you can explain a lot of mass on the lattice, what the Higgs give? Because, of course, the Higgs is very important also in giving the masses. So, and here it seems that the mass that you got, it's all electromagnetic, but there is some other component which come from Higgs. Can you tell us a little bit about that?
Sure. So for your first question regarding the status of analog simulations, I'm aware that the work has been done targeting models like this on analog quantum simulators, and I think a lot of progress has been made. I'm not probably the expert on the state of the art of that, but I think tons of progress has been made in being able to take the kind of constraints that you need to simulate gauge theories, which are special, and be able to put them on the kinds of platforms that Jens was telling us about just before. So yeah, I think lots of exciting things are happening there at MIT and elsewhere. To your second question about the Higgs, so yeah, we are here focused on relatively minimal models of particle interactions, not really trying to capture the full weight of the standard model, but instead to look at individual pieces. Certainly, it's possible to realize things like Higgs phases in theories like these, even in these simplified settings. So that that could be an answer to your question. But yeah, I think sort of the general outcome of all this is that we have tools that we can use to simulate quantum field theories of various natures, at least in this one-dimensional setting. And so we can then take those tools and use them to study Higgsing or study confinement or study all sorts of properties of the standard model that we care about.
And just a general question on the level of the standard model.
model, but what is the status? For instance, can you give us a percentage of what will be the mass given by the Higgs mechanism rather than something which is purely electromagnetic generation of masses? Do people can do that at the present state of the art?
Let's see. What is known about that from everything we have to throw at it, I'm not certain. But what I can say for using quantum simulation techniques like this to probe questions like that, so just let me say, yeah, more would be known at this stage from the Euclidean lattice. That's a technique that currently scales up better to 3 dimensions to study real-world physics. For these Hamiltonian lattice techniques that I'm telling you about, those, I think a lot of work still needs to be done on scaling them up to be able to address questions about the real-world standard model. But the hope is that this will eventually allow us to give more detailed answers to questions like those in the future.
Hi. So for this axial symmetry, so classically you have this axial symmetry when you have the mass parameter in the continuum theory is 0.
Yeah. Right.
And you said that it's broken by this ABJ anomaly, but you can get this exact answer for that parameter point. What's so special about that parameter point, given that the symmetry is kind of broken anyway?
Great question. Yeah, great question. There's been a lot of recent work on how when anomalies occur, classically they've been thought of as broken symmetries. The symmetry is gone, and yet there's always this this interesting phenomenon where we still are able to learn a lot about those theories, almost as if we had something as powerful as a symmetry at our disposal. So there's been work here at MIT studying how some of these anomalous symmetries actually give rise to more generalized mathematical structures called non-invertible symmetries. But in this particular circumstance, I think the easiest answer to your question is bosonization. So if we take the Schwinger model and then apply a mathematical transformation that turns the fermions into bosons, at that special point where the electron is massless, the boson is free. And so you just you don't have to solve any hard problem anymore.
Any other questions? Okay, let's thank Ross again.